so n is going to come out as 2. Refractive index, it can also be shown, and we're not going to show you why, you don't need to bother with the maths, but it can be shown that refractive index is also the wavelength of light in air or space divided by the wavelength of light in the slow material. It can also be shown that refractive index is sine theta 1 over sine theta 2. I'll show you that here. So if we've got a ray of light coming in, it's starting in air, then it goes into water, we know it's going to be bending towards the normal. Well, theta 1 is always the angle in air, and theta 2 is always the angle in the slow material. Can we see that we've got a pattern here? Subscript 1 of whatever we're talking about, the angle, the wavelength, or the speed, always relates to air or space, and subscript 2 is always the slow material. And finally, refractive index is 1 over sine of the critical angle. So what's that about? Well, if you are moving, if light is moving from glass into air, this situation, here is the angle of incidence, but I don't want you to think about the angle of incidence and refraction at higher. We just want to think about theta 2 and theta 1. This is the angle in the slow material, glass, and so this is theta 2. 2 is always the slow material. It bends away from the normal, and we can measure this angle. It's theta 1, it's the angle in air. You can imagine, if you keep increasing and increasing and increasing this angle here, that this turning effect is so great that there comes a point when the turning effect is so great that the ray of light just goes along the edge of the slow material. It goes along the edge of the glass, and this is known as the critical angle. Now, if you keep increasing theta 2 beyond the critical angle, then that turning effect is so great that the ray of light actually bounces back into the material. This is called total internal reflection, and this is actually how rays of light bounce down fiber optic cables. But anyway, this is the critical angle where the ray of light exits and just moves along parallel to the surface of the slow material. That's the critical angle when that happens, and refractive index is 1 over the sine of the critical angle. So how do you know what formula to choose? Shopping list. I mean, it's not difficult. If it's talking about speeds, then you're going to use that one. If it's talking about wavelengths, you're talking about that one. If it's talking about angles, you're talking about that one. If it's talking about critical angles, you're doing that one. So when a ray of light goes into a slow material, it slows down, the wavelength gets less, and there's a bend if it's not going in along the normal. But there's no change in the frequency of light. So some people think, well, some people struggle to get their head around how can the wavelength of light get shorter but the frequency doesn't change. The classic analogy is, imagine if you're going for a run, you're running along, I don't know, the towpath of a canal, and it's nice, dry, firm underfoot, as towpaths often are, so you're running at a big speed, your stride length is big, and then all of a sudden you decide you're going to veer off the towpath of a canal and you're going to go across a farmer's really, really, really boggy, sticky field. And this boggy, muddy, sticky field, it makes you slow down and your stride length will get smaller. But if you're an efficient runner, you're probably still going to try and keep the same frequency, the rate at which your feet hit the ground. You're trying to keep running at that same pace, that same rhythm, but you're still going to be slower and your stride length is going to be less. Another slightly alternative way of thinking about this is that high performance cyclists are told to try and keep their rotation rate of their pedaling rate the same, and if they're going uphill or going in difficult terrain, then they just change the gears, and if they're going in flat or something where it's easy to pedal, again change the gears again. But if you're cycling high performance, you're trying to keep the frequency of rotation, your paddling rate, exactly the same. And it's the same with high performance running. You're trying to keep your foot striking rate at exactly the same rate, but as you go into uphill, whatever, then although that frequency of rate is going to stay the same, then your running stride is going to get less, and then when you get onto the flat again, your running stride can increase, but your running frequency stays the same. Maybe that helps, maybe it doesn't. So, different materials have different refractive indices. Different materials have different refractive indices. So light going through a window, it doesn't change direction hardly anything really, because the window light is chosen, so it doesn't really have a very big refractive index at all. So light doesn't get distorted as it goes through a window pane, especially modern glass. Older glass, like really old glass in like really old pubs and whatever, light does get distorted a bit. Maybe you've noticed that if you're looking out the window while supping your pints in a lovely old oak panelled pub which you spend your Sundays in reading a book and smoking your pipe. Anyway, modern window glass, there's not a big direction change because there's not a very big refractive index, and so light rays aren't distorted. However, there are things like diamond which have a very big refractive index, and this is why diamonds are so pretty and sparkly. If you think about the formula n equals 1 over sine theta c, again, hopefully you're seeing it higher. You can play around with maths a bit to kind of focus on what you're interested in. If we're interested in the critical angle, then we can play around with that and say, well, that's 1 over refractive index. So if the refractive index of diamond is really very big, which it is, so n is very big, then the critical angle theta c ends up as being very small. Remember, the critical angle is the angle above which, the angle of incidence above which, then the light is trapped in the material, it's totally internally reflected. So if the critical angle is very small, then most incoming light to a diamond gets totally internally reflected and trapped. And this is what makes diamonds sparkle. Another example, Pyrex glass and vegetable oil have the same refractive index n. We did this in class. We put a little Pyrex beaker inside a medium Pyrex beaker inside a big Pyrex beaker, and we submerged them all in vegetable oil, and the Pyrex beakers disappeared. Spooky? No, physics. If the vegetable oil and the Pyrex have the same refractive index, then there's no speed change of the light as it moves from the oil through the Pyrex, so there's no slight bend, so there's no edges seen of the Pyrex beakers or the Pyrex dishes submerged in oil. You only see the edges of transparent things because of the new refractive index of the new material. If the new material has the same refractive index as the old material, then you don't see that slight direction change, and you don't see the edge of the material. You see the edges of transparent materials because the two materials have slightly different refractive indices, and so you get the slight change in direction. Your eyes don't realize this, they just see the edge of something, but that's why you're seeing the edge of it. Now, different wavelengths of light have different refractive indices themselves, even if they're going through the same material. So short wavelengths of light, so the blue and violet light, have bigger refractive indices, bigger n's than smaller ones. So if they have bigger refractive indices, remember what refractive index means, it means how much slower it goes, then blue and violet lights slow down a lot more. Well, if they slow down a lot more, they're affected a lot more by the slow area, so they bend more. So if we have a ray of light coming into, say, a prism, the blue and violet light slow down most, so they are bent most. The same thing affects them much more because they spend longer time in it. Whereas the red lights with the longest wavelengths are not affected as much. So when you send a ray of light through a prism, the old Pink Floyd album cover, you get red, orange, yellow, green, blue, violet. That's the order of the spectrum, and this is why the rainbow is in that order. Primary school kids spend ages singing songs about rainbows and colouring in pictures about rainbows, and the ones who enjoy colouring in pictures the most go off and do biology. But the reason a rainbow is this order is because it's the order of increasing refractive index. Refractive index gets bigger as wavelength decreases. If refractive index gets bigger, then it slows down most. If it slows down most, it gets affected most by the effect of the slow material, so it gets bent most. Speaking of biology, Biologists love looking at cells under the microscope, and you've done this in S1 and S2, and you spend your days drawing cells and colouring them in pretty pictures. And one of the most important parts of a biological cell is the nucleus in the middle. And you might remember the nucleus contains DNA molecules, and strands of DNA contain all of the instructions which get copied when the cell gets copied. So the next question then says, okay, biologists spend a lot of time, especially in school, drawing pictures of cells. What happens when we want to look at the individual strands of DNA? How do you look at the individual strands of DNA? And normal optical microscopes have a limit. And no matter how good your optical microscope, you can have the latest Gucci optical microscope, you are never going to be able to see the individual strands of DNA with it. There's a limit, and that's due to the curving or spreading out of light waves. Now, we did this in Nat 5. The spreading out of light waves is called diffraction, and it's light waves diffracting which limits the detail that optical microscopes can see. So here's a really simplified drawing of microscope lens. Here's the cell. Rays of light are coming into the lens, and if you have the thing you're looking at really close to the lens, then actually the lens doesn't form a real image behind it like it does in a camera. The rays of light actually diverge a bit, and so you can't form a real image like you do in your eye or on the back of a camera. They spread out a bit, and if you follow them back, then you end up with a virtual but magnified image on the same side as the thing you're looking at. Anyway, magnified image, and that's fine. But you get to a point, if you're looking at something so small, that the light diffracts, it spreads out, and then if you follow the rays back, they spread out some more, and then if you're following them forwards, the spreading is so great that you're not actually seeing detail, you're seeing blur. And there's a limit, I can't remember what the name of the limit is, but when you have gaps which are really small, because of the thing you're looking at is really small, then relatively speaking, the wavelength of light is relatively big, and so it spreads out a lot. When the thing you're looking at is made of kind of relatively big things, then the wavelength of light is relatively small, relatively speaking, and it doesn't diffract. And the effect of diffraction is not significant. But when you're looking at things which are really, really, really small, wavelength of light is relatively big, and big wavelengths diffract a lot, and then you get this blurring and spreading. So this is why optical microscopes have a limit. So why do we tell you all this jazz? You think, well, okay, we want something with a shorter wavelength. Why don't we use shorter wavelength light with glass lenses, for example, X-rays? Well, that's not really an option either, because solids made up of a random mix of molecules, for example glass, don't really have much of an effect on the path of X-ray light at all. X-ray light just kind of goes through them. So X-ray light isn't really affected by small things. Well, it isn't really affected by stuff like glass. However, small objects with repeating regular molecular structures do affect the path of X-ray light. And so this is how biologists look at really small things. So this is how the shape of DNA was worked out. This is what the structure and the shape of the coronavirus was worked out. It's using the process which we will see, which uses X-ray light. Anyway, we usually use visible light in the classroom, because visible light, we can see it and it's safer and it shows us exactly what's going on. So here we have rays of light coming into a gap. Now we just, in the classroom, we usually just use what they're called gratings, things with gaps in. But the principle with DNA and coronaviruses are exactly the same. There's gaps in them as well. And this is just like the Nat 5 diffraction pictures, you know, looking down on top of a ripple tank or whatever, water waves coming in, and then they come through the gap and they ripple out and they spread out. Well, these ripples interfere with each other. They run into each other and interfere, and as a result of that you get patterns